Chapter 9 in the Abstract Algebra series is the symmetric group of degree n. And problem number 1 says to convert to standard cycle form and to a composition of transpositions the following table. So let's take a look at the table. We see that in this table 1 maps to 3, but then 3 maps to 4, and then 4 maps to 5. 5 maps to 2, and then working your way back, 2 maps to 1. If we write this in standard cycle form, we will enclose all of these elements, all of these numbers in parentheses, starting with the smallest. And again, we can see that 1 goes to 3, 3 then goes to 4, 4 then goes to 5, 5 goes to 2, and then ultimately 2 wraps back around to 1. If you want to write this as a composition of transpositions, then you would simply follow this pattern. Start with the smallest element, which should be on the left, and then branch out as far as you can, working your way back toward the 1. So we would have, for the first transposition, 1, 2, followed by 1, 5. And then 1, 4, and finally 1, 3. And you can see that if you follow this pattern and do the composition working your way back from the right side, it follows the same pattern. In other words, 1 maps to 3. We can see that 3 maps to 1, and then working your way to the left side, 1 would map to 4. So 3 maps to 4. We see that 4 maps to 1, and then 1 goes to 5, so 4 goes to 5. 5 maps to 1, and then 1 goes to 2. So 5 maps to 2, and then, of course, 2 maps back to 1. Number 2, convert the following permutation in S6 to table form. This is the opposite of the first problem. This time they're actually giving us the composition of transpositions and putting it in table form. And again, since this is a composition, we must work our way from the right side. So let's see what happens to number 1. Well, 1 maps to 6. Notice that we do not have another 6 to the left, so that's the end of the road for 1. 1 simply maps to 6. What about 2? Well, 2 maps to 5, and then working our way to the left, we can see that 5 then maps to 3, and then 3 maps to 1, which means that 2 ultimately maps to 1. Let's follow 3. Working away from the right side, we get a 3 here. 3 maps to 5. End of story. What about 4? Well, 4 maps to 2. Let's follow 5. 5 maps to 2, but then 2 maps to 4. So 5 maps to 4. And then using the same pattern, we can see that 6 ultimately maps to 3. Number 3, list all the elements in S2 in cycle form and in table form. Well, the symmetric group of degree 2 is the set of all bijections on the set containing the elements 1 and 2. So here's the set for S2. And in table form, we have 2 possibilities, 2 possible bijections. One is going to be the identity bijection. In other words, 1 will map to 1, and then 2 will map to 2. And if we write that in cycle form, we would just use the smallest element inside parentheses, and this lets the reader know that this is the identity mapping. The other bijection is where they cross over. In other words, 1 goes to 2, and then 2 goes to 1. Written in cycle form, it would look like this. And again, you can see that the same pattern emerges. In other words, 1 maps to 2, and 2 maps to 1. Number 4, construct a Cayley table for S2. In symmetric groups, we need to remember that each permutation is an element, or each element is a permutation. And since 2 factorial is equal to 2, we have 2 elements, and we got these elements from problem number 3. But we said that there are two outcomes, right? We had the identity permutation, and then we had the crossover permutation, we'll say. And remember, since one is the identity, then that means that the first row is a mirror image of the top row, and then the first column is going to be a mirror image of the header column. That leaves us with our last option here. Why is 1, 2 composed with itself? Why is that equal to the identity? Well, let's compose 1, 2 with itself and see what happens. We can see, if we start from the right side, that 1 maps to 2, but then 2 maps to 1, which means 1 maps to 1. And then 2 maps to 1, and then 1 maps to 2, so 2 ultimately maps to 2, which is the identity. So this would be the Cayley table for S2. Number 5, what is the order of this permutation? Now this permutation here is just a composition, and as we saw in problem number 4, notice that in problem number 4, 1, 2 composed with itself took you back to the identity. That's because 1, 2 has only 2 components. And if you multiply 1, 2, or you compose 1, 2 with itself, it pushes each element back to its own image. If I wanted to find the order for this particular permutation, basically I want to know how many times would I have to multiply this permutation by itself to get back to the identity. Well, the answer would be 6, because if I take 1, 2, circle 3, 4, 5, circle 6, 7, 8, and I multiply it by itself 6 times, well, the first 2 times is going to take care of the 1, 2. As we've already seen, 1, 2 would map back to the identity if you square it. But what about the 3, 4, 5, and the 6, 7, 8? Well, the 3, 4, 5 would not go back to the identity unless it is raised to the power of 3. And the least common multiple between 2 and 3 is 6. So to do it 3 times would take care of the 1, 2 and the 3, 4, 5. And by default, it would also take care of the 6, 7, 8, since it also has 3 components. So if you take 1, 2, circle 3, 4, 5, circle 6, 7, 8, if you raise this to the power of 6, if you took this permutation and you took it to the power of 6, the first 2 times you multiplied it together, that would push the 1, 2 to the identity. And then if you do a third time, it would push the 3, 4, 5, and the 6, 7, 8 to the identity, but it would undo what you accomplished with 1, 2. To get all of these to go back to the identity, you would have to do it 6 times. Number 6, put the inverse of 5, 3, 4, 6, 1, put the inverse in cycle form. Well, moving to the left, we can see that 1 maps to 6, 6 maps to 4, 4 maps to 3, and 3 maps to 5. And that's what the inverse would be. 1, 6, 4, 3, 5. Problem number 7. Problem number 7, we want to take the inverse of this composition and put it into standard cycle form. Let's look at this composition in table form. In table form, we can see that 1 maps to 2, which is indicated in the first column of the table. If we want to follow 2, we'll start on the right side, and we see that 2 maps to 3. We also see that 3 maps to 4, but then 4 maps to 2, but 2 maps to 1, which means 4 would map to 1. So this would be the table for the given composition, but we have been asked to write the inverse in standard cycle form. Well, once we have it in regular form, to invert it would be to simply switch the rows and columns respectively. In other words, 1 maps to 4, which is the opposite of 4 mapping to 1. So 1 would map to 4. We can see that 2 on the second row would map to the 1 on the top row, 2 to 1, and then 3 would map to 2, and 4 would map to 3. So to write that in inverse form, starting with the smallest element, we see that 1 goes to 4, 4 then goes to 3, 3 goes to 2, 2 goes to 1, and then ultimately 1 goes back to 4. There's also a property called the shoes-socks property of groups, and it works this way. If you have a composition and you wish to find its inverse, then you simply take each component outside the brackets in reverse order, and you maintain the inverse sign. In other words, the 2, 3, 4 would come out first, and you would raise it to the power of -1 to indicate that that's the inverse. And then you would take out the 1, 2, raise it to the power of -1, and then to undo the inverse symbol, let's say, you simply reverse the elements inside each set of parentheses. So 2, 3, 4 inverse would be 2, 4, 3. And then if you take 1, 2 inverse, that takes you to 1, 2. And again, we like to write that smallest element first. And notice that if we do the composition starting from the right side, we can see that 1 maps to 2, and then 2 maps to 4. So 1 goes to 4. Likewise, 4 goes to 3. 3 would go to 2, and 2 would cycle back to 1. Okay, problem number 8. We have alpha, which is 1, 2, 4, circle 3, 5, and beta, which is equal to 6, 9, 8, circle 5, 7. And we've been asked to find a permutation gamma such that gamma alpha gamma inverse is equal to beta. The gamma composition is 1, 6, circle 2, 9, 4, 8, 3, 5, 7. And to figure that out, I used the following intuition. I knew that I was working with 2 inverse permutations, gamma and gamma inverse. And I knew that alpha had to be in the middle. So here's alpha. And notice that for gamma, I let the top row be the numbers 1 through 9, and the bottom row corresponding letters of the alphabet A through I. But since gamma inverse is on the right side, I just flip the rows and columns. And we can tell from the problem that if we multiply or compose these, if we compose these 3 permutations together, we get beta. But watch what happens if, let's say, you arbitrarily decide to see what happens with A. Let me erase here and put that back in. Let's see. Okay. So let's follow what happens to A. Notice that if you start on the right side with the gamma inverse permutation, that A has to map to 1. So that's what I indicated here, that A would have to go to 1, and then alpha will take 1 to 2, and then gamma would have to take 2 to B. So A goes to 1, 1 goes to 2, and 2 goes to B. And then I arbitrarily started with 6 in the beta permutation. And I know that 6, if 6 goes into the composition, then I know that 9 has to come out. So I chose to let A equal 6. And if A is equal to 6, then according to this mapping, 6 would have to then go to 1, 1 would have to go to 2, and then 2 would have to go to B. And we know that if 6 is the input value, let's say, that 9 has to be the output value. So at this point, I have A is equal to 6 and B is equal to 9. So then I moved over and I did the same thing, starting with 9 in beta. And I used the mapping with B. In other words, I know that B in the inverse function, in the gamma inverse function, B maps to 1. And I'm sorry, B maps to 2, and then 2 maps to 4, and then 4 has to map to D. So if I choose to let B equal 9, then 9 would have to follow that thread all the way to D, which would be 8, because 9 and 8 are paired. If you continue this process, you will eventually figure out a permutation for gamma. And this is the one that I constructed.